A ladder slipping down a vertical wall is a classic calculus related rates problem. Before we go and do this problem though, first I want to explore what happens when a ladder slips down and why this would be an interesting problem. Now it's called related rates because we have two rates going on here. One rate is the rate at which the bottom of the ladder is moving, and in this problem the other rate is the rate at which the top is moving. You might think they're the same, but take a look at this. If I move my ladder, the bottom 2 feet horizontally between 2 and 4, notice that the top does not move 2 feet as well. The top moves from just under 16 to still above 15 and a half, less than half a foot. In contrast over here, when X moves from 14 to 16, again just 2 feet, take a look at what happens to the top of the ladder. It moves from nearly 8 all the way down to 0. Now let's take a look at this ladder with the bottom moving at a constant rate, and look at that top. It goes down faster and faster, and kaboom! There it is at the bottom. So you'll see that the rate at which the top is moving is continually changing. All right, now as we do this problem, we're going to be looking at the strategy for solving any related rates problem, and we have a series of steps we're going to go through. Our first step is to read the problem carefully and draw a diagram if possible. All right, so let's go ahead and read this one. We're told that a 10-foot long ladder rests against a vertical wall. I think I'm going to go ahead and draw in the ladder in my picture below. So here we go. I've got my ladder and it's right there, and I'm going to label it with 10 feet. If the bottom of the ladder slides away from the wall at a rate of 1 foot per second, how fast is the top of the ladder sliding down the wall when the bottom is 6 feet from the wall? All right, that leads us to the second step, which is to introduce notation. We're going to assign symbols to all quantities that are functions of time. So let's take a look back over here. We were told that the bottom slides away at a rate of 1 foot per second. Now we're going to have to put some letter here to represent how far the bottom is away. And since I have this on like an XY axis, it makes sense to call this X. But what I was given was not the value of X, but dx dt. And because that's the rate at which X changes with respect to time. I can tell from the units feet per second. X is measured in feet, time in seconds, and so this makes sense. 1 foot per second. Now since I called this distance X, it makes sense to call this distance Y. Now I'm asked how fast is the top of the ladder sliding down the wall. It seems I'm being asked to find dy dt, and I'm asked to find it when the bottom is 6 feet from the wall. Now you might be tempted to put a 6 here, but it's not always equal to 6. Remember, this ladder is moving, so I don't actually want to put that value there lest I think it's always 6. So right here I'm going to say find dy dt when x equals 6. All right, let's look at our next step. In our next step, we want to write an equation that relates the various quantities of the problem. If necessary, eliminate one of the variables by substitution. It's not until we get into the problem that we'll know whether we need to eliminate any variables. All right, so let's take a look here. I have x and y, and I have 10, and I'm seeing a right triangle. So it makes sense here to use x squared plus y squared equals 10 squared. And I don't have any extra variables because see I have dx dt here and dy dt here. So I'm working with x and y. My equation has x and y. Everything looks good. All right, our next step now is to use the chain rule to differentiate both sides with respect to t. So all my derivatives are with respect to t. So the derivative of x squared will be 2x dx dt plus derivative of y squared 2y dy dt, and 10 squared is simply a constant, so I get 0. Now I immediately see that everything is a multiple of 2 here, so I'm going to save myself some work by dividing everything by 2. So I divide that by 2, divide that by 2, and 0 divided by 2 is just 0, so I'm good to go. All right, so let's take a look at what I'm supposed to do next. Now that I've differentiated, I substitute the given information into the resulting equation and solve for the unknown rate. All right, so let's take a look here. I don't know. Oh yeah, I do know what x is. Here's x. X is 6. And dx dt I was told was 1 plus, I don't know y right now, but I know, and I'm supposed to find dy dt. Well, I can't have two unknowns. So now I look back to see if I can figure out what is y at this point in time. And I'm like, oh yes, if x is 6, then I've got over here 6 squared plus y squared equals 10 squared. You might remember your Pythagorean triples or just keep working through the Pythagorean theorem, and we get y squared equals 64, or y equals 8. And so here I've got my equation. So 6 plus 8 dy dt equals 0, which means 8 dy dt equals negative 6. And lastly, I'm going to get dy dt equals negative 3/4. Now there's two things we need before we finish. First of all, units. And if I look at dy dt, that's going to tell me my units. How was y measured? Y is measured in feet, just like x. How is time measured? In this problem, time was measured in seconds. Lastly, I want to make sure, does my answer make sense? Does it make sense that dy dt is negative? Well, what's happening to y here? Y is a distance from the ground, and that distance is shrinking. Therefore, it makes sense that the rate at which y is changing is negative.